my pleasure to be here to introduce our work on thermoelectrics and hear about all of the work being done at Tel Aviv University on semiconductors. What I'm going to talk about today is the traditional thermoelectric. So we had a good introduction to transverse thermoelectrics in the last talk. I'll be focusing on the way we like to think about semiconductors and to optimize them for thermoelectrics. But for those of you who don't work specifically in thermoelectrics, the way we think about semiconductors is a little bit different, and perhaps the way we look at heavily doped semiconductors might help other research in other types of semiconductors. And what I like to do is also bring in ideas that you might have on lightly doped semiconductors, semiconductor applications, metallizations, and how maybe we can use that for us in thermoelectrics. So a traditional longitudinal thermoelectric device converts heat into electricity by absorbing heat at one substrate and then rejecting it at another. And then as the heat flows from one side to the other, it pushes the holes in the p-type material and the electrons in the n-type material. But we have to make this complicated N and P structure that we don't have to do with the transverse thermoelectric, which makes it a little bit complicated. The primary physics behind this material is the Sabacc Coefficient, which is the relationship between the voltage produced and the temperature difference. And again, for device purposes, we're interested not just in the voltage, but how much power can be converted between heat and electricity. And as was described in the previous talk, the figure of merit for a thermoelectric is this ZT parameter. So when we have our materials together, we noticed that in the previous slide we had our N and P semiconductor, and then they have to be connected at the hot side and the cold side through some metallization. And this in a generator has to be across a large temperature gradient. And often this hot side for power generation applications could be 400 degrees Celsius, or in space applications 1,000 degrees Celsius. And this leads to some unique problems that happen for us in thermoelectrics. If we look at the stresses that are formed between, for example, a lead telluride thermoelectric leg and an iron metallization on top of alumina for the hot edge, it produces quite a bit of stress, particularly at the hot junction. And when we try to build a device quickly, we see that problem show up as cracking between the lead telluride and the metallization layer in an actual module that we built. So what we're also looking at the university is other methods of metallizing to improve that connection between the metal and semiconductor. For example, there was a lot of discussion of using nickel as a diffusion barrier in these telluride thermoelectric materials, but we've noticed by putting nickel foils, pressing them on lead telluride and annealing at high temperature, we see not only the formation of nickel telluride intermetallic phases, but that the reaction proceeds via a reduction of the lead to lead liquid, which then interdiffuses into the nickel foil and makes a bit of a mess. So there's a lot of research that needs to be done for all of these new materials that we come up with to make devices out of them. So in traditional thermoelectrics, we have many applications that are known today. Most of our thermoelectric applications are in cooling, where the solid state advantage allows us to be in systems where we can do precise temperature control, even though we don't have quite the coefficient of performance. However, the way that a thermoelectric works is different from a traditional compressor-based refrigeration system, and through creative engineering, we can now start to make things like small refrigerators that have coefficient of that have the net system level coefficient of performance that is comparable to a compressor-based system. For power generation, we've seen thermoelectrics in a number of different uses. I spent almost 10 years at NASA. We've been developing thermoelectrics for power generators for spacecrafts for a number of years. Here's the Cassini orbiter that has a radioisotope heat source that converts, and a thermoelectric generator that converts the heat from the radioisotope to electricity, which powers the communication and sensors for that spacecraft. Even the latest Mars rover has a thermoelectric power supply so that it can operate at night and in the shadow of the craters. Of course, we're interested in using thermoelectrics for other applications such as waste heat recovery in automobiles. Okay, so what I want to focus the rest of this talk on is the way we look at how to optimize semiconductors to optimize thermoelectric materials. And getting back to the ZT, the name of the game is often, what can we do to improve ZT? Well, first of all, for a semiconductor, we know from semiconductor theory the approximate relationships between the Sabacc coefficient, the electrical conductivity, and thermal conductivity on many of the parameters that we can control, the most important of which is the carrier concentration. So if we look at the Sabacc coefficient versus carrier concentration, we see that that should decrease with number of carriers, and that makes sense because the Sabacc coefficient is essentially a measure of the entropy per carrier, and for lightly doped semiconductors, each carrier has quite a bit of entropy, but that reduces as the material becomes more metallic. However, the electrical conductivity is also proportional to the number of carriers, and that should increase dramatically as we go from a semiconductor to a metal. And so there's a trade-off in ZT in between a lightly doped semiconductor and a heavily doped semiconductor or metal, where the ZT peaks somewhere in between. And so often what we try to do is be able to control in this heavily doped regime. So we're typically in 10 to the 19, 10 to the 20, maybe even 10 to the 21 carriers, very heavily doped semiconductor. And so in order to do that, we need to use extrinsic defects to produce quite a large number of carriers in our semiconductor. And so the simplest way to do that for us, we have a slightly simplified way of thinking about doping. We are putting so many dopants into our material that we simply count the number of extra electrons from the atoms that go in, from the extrinsic dopants, and that can, in many instances, simply correlate to the number of carriers, even up to 10 to the 20, 10 to the 21 carriers. So, for example, in lead telluride, replacing a tellurium with an iodine adds an extra electron, while the number of states remains the same. So our simple picture of our conduction band and valence band is essentially the same number of states, but we've added more electrons that fill up the conduction band. And we measure from Hall effect the number of carriers for each iodine atom that goes in there, and we get a good correlation up to 10 to the 20 carriers. And so this allows us to adjust the transport properties of these semiconductors. Now, these materials have resistivities which are increasing with temperature, and so these are heavily doped semiconductors that look almost like metals. Through this doping, we can adjust their resistivities, and then we get Sabacc coefficients that are also relatively large and also change linearly, and this is typical, again, also of a degenerate semiconductor. And by increasing the carrier concentration, the Sabacc coefficients can get quite small. You might recognize those Sabaccs closer to a metal, but yet we're going to understand these as heavily doped semiconductors. For the thermoelectric properties, we also need to understand the thermal conductivity, and the thermal conductivity of a semiconductor includes the electronic contribution, so we need to take care of that, and there's also some bipolar thermal conductivity that will come in as well. One of the things we like to do is since we use these at high temperature, we need a high temperature band gap. The Sabacc coefficient is a very nice way of measuring the band gap. When we see the Sabacc coefficient roll over, we can correlate that with the electronic band gap. Okay, so one of the simple principles that we use in our heavily doped semiconductor is the concept of rigid band doping. So we think of our thermoelectrics as having a valence band and a conduction band and a valence band that doesn't move depending on our extrinsic dopants, and we can dope them hole type or electron type. If we do some calculations, we can see that many of the dopants that form very easily can also be understood simply as a rigid band system where if we look at the density of states, they're essentially the same. Some dopants, though, such as thallium in lead telluride, can affect the density of states in the band gap region, and so that's not going to be a simple rigid band dopant. But for the most case, we've got rigid band. So a simple example of doping in lead telluride is if we add excess lead, that produces tellurium vacancies. In each of those vacancies provides 2 extra electrons. If we're excess lead, for example, we can have lead vacancies, and that gives us 2 holes. And in lead telluride, depending on how we make it, we can either have extra electrons with excess metal, or we can have extra holes. And so we make this sort of phase diagram of lead telluride, which allows us to adjust the number of holes or electrons with temperature and chemical potential. So we use the lead to tellurium ratio to adjust the chemical potential, and then the temperature, we can adjust the number of defects. Now, it's really difficult to measure those small defect concentrations chemically, but we can measure it with the Hall carrier concentration, and now today we can calculate them from first principles defect calculations. So we can, for example, calculate the enthalpy of each defect as a function of the Fermi level or electron chemical potential, and we can predict what types of defects will form when we're in the band gap region. And so in lead-rich, we can calculate indeed that we have tellurium vacancies. In the tellurium-rich regime, we can calculate that we have the lead vacancies as the predominant type of defect. And what that allows us to do then is to take what we would normally just see as a simple phase diagram, of a line compound for lead telluride between lead and tellurium. We can blow that up, and we actually can map out the true phase diagram width of that material, and we can from the calculations as well as the experiment see that there's a width that explains why we can make both N-type and P-type. So with that knowledge, we can start to understand the intrinsic defects that happen in many of these materials that are more complex. And so, for example, we look at new complex semiconductors because these have more knobs to adjust the material properties. And one example is this 1-2-2 type structure. example is a terbium zinc 2 antimony 2. And the pure form of it should be a simple semiconductor, but when we produce the material, we end up with some ytterbium vacancies, and that reduces the Fermi level and gives us some holes in the valence band. And what we've noticed is that this defect concentration is variable, and we can draw that in terms of a phase diagram like we did with the lead telluride, where the shaded region is the allowed range of ytterbium content, and all of this shaded region lives to the left of the pure compound, meaning that this material is always p-type, and the carrier concentration can be adjusted only within the shaded region. And so now we have some recent data that shows that, yes, indeed, we can adjust carrier concentration between 10 to the 20 and into the 10 to the 19s by moving within this shaded region. Okay, so with that understanding that these defects are actually equilibrium controlled, that the defects can be calculated from first principles, we can go back to our structure and propose that that this ytterbium vacancy has a bit of chemistry to it, and we can calculate that that, for example, the calcium version or the europium or the strontium will have slightly different vacancy energies, and then calculate this phase width for the different materials. And that allows us to explain why we see now a trend in the number of free carriers that we have in the material versus the electronegativity or the chemistry of that cation. And again, this is a very powerful way of adjusting the carrier concentration in the material, which then optimizes the resistivity and the Sabacc coefficient. So we can get nice high Sabacc coefficient in materials with reasonably low resistivity using the chemistry of that cation, which simply adjusts the native defect concentration of those materials. And so this is one example in a relatively new semiconductor, and we can then use that to look at other materials. So this zinc antimonide was a very complicated material that has a very high ZT, and we were curious as to how that material gets doped. And so if we go back to the DFT again, like I said, we can't actually calculate, we can't measure the differences in zinc content, but we can calculate them from first principles. We can calculate how much this delta, what zinc deficiency that we actually have in thermodynamic materials. Now, so this zinc 4 antimony 3 is actually 3.9 minus delta, and using these calculations we can show that the phase diagram should look something like this blue shaded region, where the experimentally observed carrier concentrations are in orange. And so for first principles calculations, this is actually pretty good. And this explains, again, why this material is always p-type. It's always zinc deficient compared to the semiconducting composition. So the other thing that this understanding of phase diagrams brings out is also a bit of understanding about processing and microstructure, because what we see here is the temperature dependence of the solubility of the zinc, which means that if we change temperature, we ought to make things like precipitates that form out. And so on the zinc poor side, we have zinc antimony precipitates that form, and we see that on this side. On the other side, we should have zinc-rich precipitation. We have extra solubility of zinc at high temperature that should lead to zinc precipitates at lower temperature. And there's even a retrograde solubility regime that leads to zinc precipitation spreading, forming those zinc particles that then reabsorb into the material, and we end up with these nanovoids in the material. Okay, so that kind of microstructure is good for reducing lattice thermal conductivity, and what we found is that by understanding the phase diagrams, we can go back to material science and say, well, we can use that to control microstructure for lots of different reasons. So one of our favorite systems to study is the phase diagram between lead telluride and antimony telluride, which has a very simple eutectic, but all materials are actual solid solutions, and so on either side, this material here is actually lead telluride with some antimony dissolved in it. And there's 3 different examples here of different ways to make microstructures. One is simply by taking a liquid and fast cooling it, we can make this microstructure of the 2 eutectic type materials together. This will have lower thermal conductivity with the finer microstructure. What we also find is that we can get some eutectoid decomposition with this small phase that lives in here, and when that material decomposes from a solid state reaction, we can make a natural superlattice type material, and this is perfect for the previous talk because this is actually a type 2 superlattice of an N-type and a P-type material together. And then the last example is the solid state precipitation, which is what we saw with the zinc antimonide, where we've got nanoparticles coming out of a solid solution. And when these precipitate in the solid, we have good epitaxial-like arrangement of the interfaces between there. You can see from the ordered structure that there's crystallographic alignment. Okay, so moving on to optimizing the material now. So we realize we can adjust the carrier concentration with doping. We want to get to this peak ZT value, but now we want to optimize the material. What can we do to get the highest peak value? And that means we need to look at the material properties that determine this peak ZT value, and we call that the quality factor. So we're going to get rid of the carrier concentration parameter, and we're going to find that the quality factor depends on properties of the band structure, the effective mass, the number of valleys in the number of conduction pockets in the Fermi surface, and then the lattice thermal conductivity. So just to give a quick example of what we can do there, we're going to talk about how we can engineer the band structure with alloying. So the idea here is that the number of valleys is an important factor of the quality factor, and that means we're looking for Fermi surfaces with lots of discrete pockets in them. And one way to do that is to look at a band structure where we might have a heavy hole and a light hole, but separated by an energy, and if we can move them together to get them to the same energy, we can have an improved quality factor because we've increased the number of pockets in the Fermi surface. So an example is lead selenide when alloyed with strontium selenide. Lead selenide is a very narrow gap semiconductor. Strontium selenide is much higher band gap. That opens up the L pockets to be closer to the sigma pocket, and we can see the change in band gap optically as we increase the strontium content. We can also compare that theoretically. What we see when we do that is the Sabacc coefficient goes up because the density of states, there's more carrier pockets contributing to the entropy, which raises the Sabacc coefficient, and that helps, obviously helps the ZT. So we can get to now ZTs as described well above 1. We can get ZTs around 2 using these carrier pocket engineering approaches. Okay, so to summarize, we're looking a lot at defects in semiconductors to control the carrier concentration. We're using the extrinsic defects, looking at the charge valence to engineer the carrier concentration, and also the intrinsic defects that come naturally from the phase diagrams. And that leads to an important understanding of, or it leads to the importance of understanding the phase diagrams, both experimentally and utilizing calculations to predict them. These phase diagrams control microstructure, which we can utilize for phonon scattering, that allow us low lattice thermal conductivity, which we need for the quality factor. And then in order to optimize the material as a whole, we need to focus on the quality factor of the material, which includes these 3 parameters. We need lots of carrier pockets, high valley degeneracy, so a Fermi surface with many different pockets in them. We need a light mass for good conduction, and then we need this low lattice thermal conductivity. And in the end, we need to make sure that if we're going to do something that scatters the phonons for low lattice thermal conductivity, we need to make sure that we don't disrupt the mobility, and so we need to balance that with this quality factor. Okay, so that was quite a bit. I'm happy to take questions and discuss some of our other results, and maybe you can give us in our field some suggestions on how to optimize semiconductor materials and devices. And thank you for your attention.
Questions, please?
Yeah, so you limited the work you talked about to the rigid band model, but I'm wondering for the case where you have the dopant that's resonant, it starts to perturb the band structure. Could you think about that also in terms of the quality factor?
Yeah.
The benefit it can give, and so what's your opinion on which might ultimately give a higher ZT?
Well, yeah. So that is a tricky point, and the way we like to think about it is that if the new states, so for example, the resonant states that would come in, if they produce new carrier pockets, then that's an advantage. But if they are simply increasing the mass, which would flatten the bands, give you a higher Sabacc, but it's not going to give you an overall greater quality factor, is not going to be advantageous. So if those states are going to produce new carrier pockets, then it's good. Yep.
Assuming you solve all these problems, you still have the contact issues. Is a meet here? No, this is not here. I think I have some ideas how to make better contacts, better barrier, like double barrier. So I would be very happy to talk to you.
I'd love to talk about that. Yeah.
These defects that you're deliberately introducing into these materials, probably they're at such a small scale that maybe it doesn't matter. But if they're putting these at a task where they're in an automobile or there's some place where they got so hot, and then once they're in my garage overnight in Chicago, they're so cold. So when they cycle,
Yep.
When they go through thermal cycles,
Yep.
would that make them more vulnerable to mechanical stress due to thermal cycling?
The mechanical aspect, I don't know, but the temperature variation should lead to dopant precipitation. So we've seen this. So none of these materials are thermodynamically stable, right? So at low temperature, they're all kinetically stabilized. The dopants have solubility that increases with temperature, and at low temperature, most of our materials, the dopant isn't actually soluble anymore. This turns out to be a problem that's that's not really well discussed in the field, but actually quite known in the materials that we've used on spacecraft. So the silicon germanium that we use on Voyager, for example, is doped to 10 to the 20 carriers, which is a huge number of I think we use phosphorus, for example, right? I don't think you can normally get to 10 to the 20. So you have to go to high temperature to get that in there. We anneal it at high temperature and then quench it. We freeze those dopants in. But when the spacecraft is flying, regions of the material are warm enough to give mobility so that the dopant precipitates out, but it's low enough temperature that it's actually thermodynamically supposed to come out. So we have this window of opportunity where the material starts to degrade a little bit. And as long as we know how fast it is, we can calculate it for the lifetime of the material.
More questions? Okay, so thank you again.